focal point has to meet with the back of the retina if we want to see clear. Otherwise, if it is in front of the retina or behind the retina, then the image looks out of focus, fuzzy, right? And so the rays arrive parallel, they converge, and they arrive to the back of the retina, creating therefore your focal point. The distance between the lens and the focal point is called focal distance, okay? And then at the angle that they generate when they bend the rays, this is called the angle of refraction. So what is refraction? Refraction is the ability to bend the rays, the ability to bend the rays, whether converging or diverging, doesn't matter, is the ability to bend the rays. What is actually going to create the refraction portion? There are two major things that are going to be creating refraction, or in other words, ability to bend. And I have brought it down there. The ratio of the refractive indices. You guys took physics? That was a question. Do you guys take physics? Yes, right? So you guys remember some of this stuff. What is the index of refraction? The index of refraction basically is the ability to bend the rays when it's changing the medium. So if it goes from a medium that is little dense to a medium that is more dense, then the rays are going to travel slower. That is going to bend the incident rate, is going to bend the refractive rate towards the normal. You guys remember all that. And so, when we want to know whether the bending of the rays is going to happen, then you measure the index of refraction. Each index of refraction is basically just very simply the speed of light in vacuum, is the ratio of the speed of light in vacuum to the speed of light through the medium that you are trying to measure. And then in vacuum is supposed to be basically the highest. Nothing is going to be faster than the highest, or so that we think, right? And so therefore this refraction number is always positive. And the other part that we also need to consider is the degree of angulation. What is the degree of angulation? Well, notice over here, these rays that are arriving to the edge of this lens, they refract. This ray that is arriving to the edge of this lens, they diffract. But the ray that is arriving right through the center doesn't bend at all. And the reason of that is because arriving perpendicular to the plane of the lens. So when it arrives at an oblique manner, right, that is angulation, right, then it bends it. And the more oblique it is, the more it's going to bend. So these two are the major factors that are going to determine the refraction in a lens. Okay? Let's take a look first at the refractive indices. In our eyes, we don't have the biconcave or concave lens. We don't even have the convex lens. We have the biconvex lens. That's what it is in our eyes. In a camera, you also have a biconvex lens. The camera focuses far and near by moving the lens forward and back. Our eye doesn't do that. Our eye has to do in two elements that are going to cause bending of the rays. The major two elements that are going to cause bending of the rays, one is going to be the cornea, and the other one is going to be the lens. The cornea will be a fixed bending. You cannot change that. In other words, you cannot accommodate to an object being far or close. You cannot accommodate, it's fixed. And whereas the lens changes shape, causing therefore the bending of the rays to increase or to decrease, depending on how far is the object. When the object is closer, it has to bend the rays more. So therefore, it creates the focal point right at the retina. Otherwise, the focal point falls behind. That increasing or decreasing of the bending has to do with the degree of angulation. All right, because let me go back. Let me go back. Okay, so here, the lenses. Let's assume first that the lens doesn't change shape. In other words, we are going to take a look only at the refractive index. We are going to put aside the degree of angulation. So what happens when the lens doesn't change? Now, the light path of whatever we are seeing has to go through the following. First, it's going to go through the air. Then it's going to have to go through the cornea. That means there is an interface between air and cornea. which one is more dense, the air or the cornea? The cornea. So therefore, it's going to bend towards the normal. Remember, you're going to bend it towards the normal because it's going to slow it down. Then it's going to have to go from the cornea into the aqueous humor. Okay, and then from the aqueous, so there's another interface between the inner portion of the cornea and the aqueous humor. And then it's going to have to go through the lens. So there's another interface between the aqueous humor and the outside of the lens. Okay? And then it's going to have to exit the lens and go into the vitreous humor. That means there is another interface between the back of the lens and the vitreous humor. And finally, we will arrive to the retina. If we measure the refractive indices of all of this, it looks something like this. Do you notice something? Take a look at it. Did you notice something? Okay, I need to move. Let me give you a push. Which one is the most striking difference? Which interface is the most striking difference?
Air to cornea.
The what?
Air to cornea.
Air to what?
Cornea.
Air to cornea is the most striking difference. In fact, the other ones is negligible. The bending is basically almost non-existent. It does have a bending, From the physics point of view, you can actually measure and all that, but for the clinical purposes, it doesn't really bend, right? Because it's negligible. And so the only thing that here matters is going from the air through the cornea, and that is going to create the maximum bending that is going to happen. If we put all these together, if we are able to add them algebraically, of course, okay? We're going to go into the algebraic equation or anything. If we can add it, then we're going to have a total in the eye of 59 diopters. Diopters is a measurement of the inverse of the focal length in meters.